I will say that the times when I've seen that, it's generally been with the library. It's never been with the registrar. So it's never been grade information or student information. It's been, yeah, do I really care if somebody knows what book search I made? Well, I probably don't care very much about that. So, you know, one of the primary things about security is that the effort you make to be secure should depend on the value of what you're securing. And I've never seen that with registration information or grade information or something like that.
This doesn't so much have to do with the wireless stuff, but what about the university using stuff like Biddle, those Latvian site reports?
It's stupid.
It's stupid, yes. I'll grant you that. I mean, if you see a web address and it's .ly at the end, what does that ly stand for? Libya. Libya. And we know what wonderful folks the Libyans are.
Person trying to steal your bank information have to, do they have to decrypt the information itself?
Yes.
Repeat the question.
He's asking about stealing bank information, and when you're doing banking, typically you will set up one of these encrypted connections at the beginning of your session with the bank, and it will be encrypted information flowing both ways, both from you to the bank and from the bank to you, until you either close the browser or log off. So, like I said, I'm unaware of any fraud ever perpetrated on the basis of breaking that encryption. Sloppy certificate management, that's a different story. He's reminding us that several years ago the university had a major data security breach in which a lot of alumni and student information was compromised, including social security numbers. Let me say that encryption is a good way to get something from here to there without being compromised in between. Once it gets there, the encryption becomes a matter of storage. Is it stored securely? And in this case, no, it wasn't. So it was not that any of this stuff was stolen in transit. It was stolen from the database where it was stored on a server. It's 5:45.
So we've got actually a second part of this I want to talk about. Our barbarians are here. If you want to know if they can see something you're doing in 20 minutes or so, Samuel.
Yeah, before we move off of that, just also keep in mind, folks, that we can see what websites you're going to too. So, you know, if you're browsing for, I don't know, porn or whatever, all your neighbors, if you're in the dorms, probably half your dorm can see that. You know, over the course of this talk, I've seen people going to ESPN, to Apple's website. So, yeah, just keep that in mind. All the URLs, everything's out there too.
So if you want to see how these things work, these guys are going to be around after. I encourage you to come by and take a look at what they've done to find out what you're doing, because that's part of what we want to do here for fun.
Another question.
Yeah, question.
The username and password you type in for logging in to the site, are those encrypted data too?
The username and password you type when going to a website, are they encrypted? That all depends on whether or not the padlock is there, essentially. By default, you're just typing into a web page. There's no reason in the world that would have to be encrypted. If you don't see the padlock for the end-to-end encryption we were talking about, then it's probably not encrypted.
Because for I can use, if I have a password that is more than 8 characters, I have to type in the whole password. But when I go into webmail, if I get the first 8 right, then I can actually log into my webmail. Even though my password is
So
greater than 8.
the question is about lengths of passwords and stuff. I have a longer answer for that. If you wanted to talk about it offline, we could. It has to do with different computer systems probably and how much of the password they're interested in. So I do want to go on to the second part of this talk. What we're talking about is the kind of stuff that we talk about in a lot of our classes, but the other thing that they want us to talk about is research sorts of things, the things that we're doing in the lab. So we're using that information to work with NASA on interplanetary networking. And Dr. Kruse is going to tell you more about exactly what we're doing with NASA in a little bit. But I want to see if I can motivate the problem for you. So what we're doing work on is called DTN, Delay and Disruption Tolerant Networking. And I'm going to talk about the disruption part, and then we're going to bring back Phil to talk about the delay kind of part. So there are lots of different ways that people do disrupted communication, sensor networks and kind of stuff. The most fun one to talk about is the one I'm going to talk about today. And I'm only going to talk about it for a few minutes. But this one is really easy to envision. There was a problem at Princeton. A computer science professor who was interested in wireless networking ran across some biologists that were interested in tracking zebras in Africa. Now, the zebras don't have so many iPhones and stuff, but what she wanted to know was, where do the zebras go? Where do they spend their night? An average zebra, what's its range? How many hours a day do they spend eating versus sleeping? Does it matter if it's sunny? Are they more likely to walk if it's shady? Sunny? All sorts of interesting things you might want to know if you know a lot about zebras. The problem is that the technology that's typically used for that, you've probably seen nature shows where they have the radio collars and stuff, that's VHS kind of stuff. And you'll see the guys driving around in a Jeep with this directional antenna. Okay, the zebra is sort of that direction. Drive 10 miles that way. Okay, and you go 10 miles, and okay, now the zebra is over there a little bit, so drive another couple miles. And maybe you'll run across the zebra. And now you know where the zebra is, but you don't know where it was yesterday, you don't know what it's been doing. So what they wanted to know was, could I track information about these zebras and do something useful? So what they did is they came up with a system that essentially put a GPS receiver on the zebras and a little bit of a computer, and so they could keep track of where was the zebra over the last, well actually they ran the experiment for a year was their plan. Can I figure out where the zebras were, what they were eating, what they ran across, did they ever go into farmers' fields, did they ever hang out with other kinds of zebras? I don't know much about zebras, sorry. The problem was, there's no good way to get the information back from the zebras, because this is the middle of some savanna someplace, where there's no infrastructure. There's barely any infrastructure for some of the people who live in the small towns there, let alone the zebras. So what they did is they came up with a system of ad hoc networking, and the idea is each one of those computers on the zebras has a very small radio transmitter receiver on it. Now, you can't afford to talk to a huge satellite far away, although that's technically possible, but it would be expensive, one, and it would use a lot of power, a lot of electricity. The zebra harnesses do have solar panels on them, so they can drive a little bit of power, but not enough to talk to a satellite in geosynchronous orbit. So what they wanted to do was come up with a system where the zebras could talk to things nearby, think maybe 100 feet away. And so ZebraNet was born. And the idea is, cool stuff. It's fun to think about, right? So imagine you're a zebra, you've got this collar on, you're wandering around, I'm collecting information about what I'm doing, is they keep track of whether their heads are down or up, and somehow they can tell if they're chewing, I didn't ask. And so you get all this information. Then when two zebras get next to each other, if they both have these transmitters on, they'll exchange information. So Hans here, he's wearing black, he looks a little like a zebra there. So he's going to send me, or his caller will send me all the information about what he's been doing, and my caller will send him the information about what I've been doing, and now we both have that information. And now I'm going to wander over to the water hole because I'm thirsty, and I'm going to exchange information with Phil here about where he's been. I'll tell him where I've been, but I'm also going to tell him what Hans has been up to. He was eating all day yesterday. It was a day off for him. So what's going to happen is all this information about all the zebras is going to get through this entire zebra network. And then somewhere on the savanna, near a watering hole or something, there will be one antenna, so that when I water next to this special tree, my antenna will download all the information I've collected about all the zebras I've run into to a single access point that will save it all, and then the researchers can just drive up to that tree, basically plug in and get all the information about all the zebras. So that is disrupted communication. None of those zebras, well, is typically going to be close enough to that tree that I can get all their information all the time. And some of the zebras never go near that tree at all. They're 100 miles over that way somewhere. But they've run into zebras that have run into zebras that have run into me, and somehow the information gets where it's supposed to go. So that's the whole idea that we're dealing here with disrupted networking. I can't do a video chat that way necessarily, not a live video chat, but I can get information from place to place, even though the little hops in between are not in constant communication. So thinking about zebras is kind of cool. Something compelling about zebras at a water hole, you can imagine the problem. Now, if you need something a little bit more practical, they actually use this same technology in a program called Bytewalla, which is also an African-based process, except that they are communicating email messages and video snippets from Android-based phones. Android, the Google, the cool phones. And they're using the same technology in small towns and villages so that I can have my Android-based phone. I don't have any cell phone infrastructure necessarily, but I can still type up an email. Now, when the bus comes by or something going to the next village, that bus will talk to my phone, it will exchange email back and forth, then that bus will go to the next village, and who I'm trying to talk to is the next village, it'll eventually get where it's going. So it's the same process without the zebras, is that we can have disconnected, I don't know if you can talk to a zebra that way. Anyway, let's assume they're distinct populations. So the idea is, without being in constant communication, you can exchange information back and forth, and you can get sort of end-to-end communication, even though I'm only talking to things 100 feet away. So that's the whole point in the D for disruption-tolerant networking. So that doesn't get us to Mars or anything, but at least it'll get us around a little bit. Phil, what do you know about delays? Nice try.
The other day I told Shawn I could do 10 minutes on orbits, and I'm sitting there and I'm thinking low Earth orbits and medium Earth orbits and geostationary orbits and geosynchronous orbits, which are not the same, and Lagrange points and relays, and then I said, you know, I could do 10 minutes, but it wouldn't be 10 entertaining minutes. So let's just say that there are two important facts here. Light is really fast, but it's not infinitely fast. And the solar system is really big. So here on Earth...
Class lasts an hour?
Pardon?
Your whole class lasts an hour and that's the whole spiel?
So the solar system is really big. And the terrestrial internet, and I'm not sure if this is on either of your agendas, the terrestrial internet works a lot with acknowledgments. I send something, and if I don't get an acknowledgement back from the destination, I send it again, just to be on the safe side. That's how we get reliability. And it's how when intermediate parties lose or garble the information, I don't get an acknowledgement back, and I retransmit it. And that whole process takes milliseconds, because light is really fast, and the Earth isn't that big. On the other hand, when you start going to the moon, and you start going to Mars, which, depending on where Earth and Mars are in their orbits, there's quite a range of light travel times, but it's the right unit to think of is minutes. And you get to the outer solar system, and the right way to think about it is hours or days. Then suddenly